Welcome, everyone. For today's prep, we're going to start to look at some applications of derivatives. So we've been learning all these derivative rules and what the derivative actually is, but now we're going to start to put it to some use. And the first application we're going to kind of look at is kind of has a graphical spin to it. So we're going to be looking at how do we find the intervals of increase, decrease for a function. And we're going to start with graphically. How do we graphically find the intervals of increase, decrease? And then in the next section, we're going to see how do we use our derivative to help us find the intervals of increase, decrease. All right. So let's start by just defining, well, what does it mean for a function to be increasing or decreasing? So we say that a function is increasing on an interval if the graph continuously rises. So if we take an x value and plug it into the function, and then we take a larger x value, the output for that larger x value is bigger. So the function value goes up. So the function value rises, it goes up. Now, a function is decreasing if we take, same thing, we take one x value, plug it into the function, take another x value, plug it into the function, and that bigger x value gives us a smaller function value. So what happens here is the inequality kind of changes, it goes down. So a function's decreasing if our function values are falling. So our function value goes down. All right, so there we go. It helps if you could see. So increasing, decreasing. Increase, our function is kind of moving up. Decrease, our function value is moving down. All right, so this is kind of the precise definition of increase, decrease. But, we have some intuition when we look at the graph. So let's look at just some examples here of, we have a few different graphs. And we're looking at one particular place, x equals c. And we want to know, is the graph increasing, decreasing, or neither there? So let's look at the first one. Here's the graph of a function. And we're looking at x equals c, and we've plotted the point. So let's draw our tangent line at that point. So maybe something like this. So we got our tangent line. And we see that the tangent line is moving up. So it has positive slope. It's moving up. So our graph is increasing in this case. Okay. Well, let's look at the next one. So here we have a similar function, different point that we're looking at though. So we're looking at this point right here. And this point is kind of right in the middle. It's right at this kind of rounded bend here in our curve. And what happens if we were to draw the tangent line? Well, the tangent line, try that again. That's better. Tangent line would be horizontal. So again, this is our tangent. And it's a horizontal, so this would be neither. So in the first case, if we were to think about, well, what would be the derivative at this x value? The derivative here would be positive, because our tangent line is going up. Here, what would happen here? Well, the derivative value would be 0 at this point, because it's just a horizontal line. So we'd say it's neither increasing or decreasing. And then our last example, same function, now we're just looking at a different point. So again, if we want to know if our function's increasing or decreasing, let's draw a tangent line, and we can just see, well, where is that tangent line going? So maybe something like this. We got our tangent line, And in this case, if we were to think about what f prime is, well, our tangent line is pointing down, so our derivative would be negative. And since our tangent line is pointing down, we say our function is decreasing at that point. Okay. So being able to kind of pick out where a function's increasing, decreasing is going to be helpful. Now, there are a couple other points that we're going to be interested in, and these are places where our function has a high point or a low point. So let's kind of graphically look at these, and then we'll come back to the definition. So two graphs here. Again, we're looking at this place x equals c on each of these graphs. And in the first graph, we notice that this point is kind of higher than all the, well, not all, but all the other points in the surrounding area there. So in this case, we would call this a relative maximum. At x equals c. And it's kind of a high point on our graph. And then in the second graph here, this is an example of what we would call a relative minimum, because it's a low point. We also use the word local, so you might see local instead of relative. Oh, we do use relative. So we got both, relative or local. We use those interchangeably. So local maximum, local minimum. I kind of like local better because it kind of gives you the idea that we're just looking in the surrounding area. We're not necessarily considering the entire curve. We're just looking in this immediate area. That's the high point. So the definition for a local max is our function value at that high point is bigger than all the surrounding function values for x near c. Kind of the key word here is x near c. That's what makes this local. We're not looking at all x values. We're just kind of looking in the surrounding area. And then for local minimum, the function value at our point is smaller than all the surrounding x values. So again, local, we're just looking near c. So you can imagine, way to kind of imagine a local max and a local min, imagine if you were standing on the curve. So we're standing here, and if you're standing at that point, it's downhill in both directions. So that's a maximum. If you go downhill in both directions, you're at a high point. At a local minimum, or a relative minimum, it's uphill in both directions. Okay. So let's try out an example. We're going to look at example 2. We're going to be given the graph of a function y equals f of x, and we're going to figure out all intervals where this function is increasing and all the intervals where it's decreasing, and then we're going to locate all the x values where our function has a local max or local min. All right. And let's actually start with the x values where we have a local max or local min. So we go to our graph. Here's our graph. So we want to find all the places where we have a high point or a low point. So on the graph here, as we're going left to right, imagine just kind of tracing along the curve, and then we get to this point right here. And again, if you were imagine just standing on the curve, it's downhill, downhill. So x equals -2 is a local maximum. So let's kind of really denote that along the x-axis there. So let's keep a running tab of all our maximums. We'll maybe put it over here. So our local max. So we have a local max at x equals -2. Okay. So then, and let's keep a tab for our local mins as well. We haven't encountered any of those, but we found that we have a local max at x equals -2. So then as we keep going, then we hit this kind of sharp point here, and we change direction. So again, if we imagine kind of standing at that point, it's uphill if we move to the left, it's uphill if we move to the right. So when we go uphill in both directions, that's a sign that we have a low point. So we have a local min at x equals -1. So something special is happening at -1 as well. So let's kind of mark that on our x-axis. Okay, so we keep going. We're going up, 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 up. And then we hit a high point right here at x equals 0. And again, you want to think of it, imagine if you were up there on the curve, downhill, downhill in either direction. So we have a local max at x equals 0 as well. So usual, something special is happening here. So let's mark that on our x-axis as well. All right, so then we keep going. And we're going down, 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 down. And then we level out, and then we change direction. So we see that here we have a local min. So if we were standing at this point, it's uphill in both directions around that. So we have a local min at x equals 3. And let's mark that on our x-axis as well. And then once we get past that local min, then it looks like it's uphill from there on out. Okay, so this looks like we have, for kind of, what color do I want to use? I guess we'll use green. All right, so it looks like we have a local max at 2 spots. We have a local max at this point, and we had a local max at this point. And then we had a local min also at 2 spots. And we had a local min here, and we had a local min here. Okay, so we found where our function has these maxes and mins. So now let's figure out the intervals of increase. And the intervals of increase and decrease, it's these maxes and mins are going to be helpful. So that why we were keeping these kind of marks along the x-axis is because these maxes and mins are a lot of times where our function changes from increasing to decreasing. I shouldn't say a lot of times, it's always where our function changes from increasing to decreasing or vice versa. So if we look at this first section of our x-axis, this section here, what's going on at all the points? Well, all the points are moving up on that section of the x-axis. Now what about in here? What about that next interval? Right in there. Well, on that section, all of the points were moving down. And then on the next interval, same kind of deal. We're moving back up. So at all the points our function's increasing on that section. And then over here, we're decreasing. And then finally, once we get to that local min, then our function was going back up again. So this section of the x-axis was increasing. So these maxes and mins are kind of splitting up our x-axis, essentially, into these intervals of increase and decrease. So on this interval, we would say our function is increasing. On this interval, we would say decreasing, and then increasing, decreasing, and then back to increasing. So how would we write this out? So intervals of increase. Well, what did we find? Well, we found this whole section of the x-axis. So kind of going from the minus infinity direction all the way to -2. And when we do this, we're going to use open intervals, so we're just going to use parentheses on both sides here. Then we found this interval in between -1 and 0, so we're just kind of listing these, so -1 to 0. And then finally, this one goes from 3, and it just keeps on going in the positive infinity direction. So we go from 3 to infinity. Now, what about the intervals of decrease? Well, we found 2 of them. So everything in between -2 and -1. So we'll write that as an open interval, -2 to -1. And then we found right in here, 0 to 3. And there we go. We located the intervals of increase, decrease, and we found all the local maxes and mins. All right, so we're going to practice this a little bit more in class, and then we'll see how to use the first derivative to kind of pinpoint these intervals for us. All right, so we'll see you then. Bye-bye.